All right, so I made an example problem for an integrated problem that's probably more involved than what you would run across, but I always think it's better to make something a little bit bigger so you see more things that could come up rather than like a small short example. So I'm sticking with this more involved problem. Like I said, you might not have to do as much for your own integrated problem. So in this problem, I have a block that's traveling up an inclined plane. It has an initial speed of 10 meters per second, but there is friction between the block and the ramp. The coefficient of kinetic friction is 0.2. I'm going to let the block go 2 meters along the length of the ramp, but then it reaches the end of the ramp and it's going to fly off into space. And that's going to be part of the problem as well. So the first part of this problem, I want to figure out how fast it's traveling when it flies off the ramp. So when it gets to here, I want to know how fast it's going. In order to figure out that, I need to know its acceleration along the incline, and to do that, I'm going to use forces. So I'm going to identify the forces acting on this block. There's the normal force, there's gravity acting straight down. And because it's moving up the ramp, friction is going to be down the ramp. So now I'm going to apply my laws of motion. In the y direction, my forces add up to be 0 because the block is not moving from the surface of the ramp. So I have normal force minus the y component of the weight, which is mg cosine of 20 degrees. So my normal force is equal to mg cosine 20. I'm going to need that in order to find my frictional force. Now for me, I know it's going to accelerate down the incline. That is, it's slowing down as it goes on the incline, so the direction of the acceleration is towards the bottom. So I'm going to look at forces in the x direction and see if I can find out what that acceleration is. I'm going to actually make down the incline be my positive direction just to get rid of negative signs, because my forces that act in the x direction are both in going down the incline, as is my acceleration. So I have frictional force plus the x component of the weight are the forces acting down the incline. And that's equal to my mass times my acceleration. Everything here is positive because I chose down the incline to be positive for this part, and everything is in that direction. They're all in the same direction. My frictional force is mu k times the normal. And I know what my normal force is, mg cosine 20. I noticed a lot of you like to calculate the force of friction and the normal force before you start into the rest of the problem, and that's all well and good, but I would say that's a total waste of your time. If I get to this point, notice that I see that my mass cancels out all the way through, and so those calculations were really didn't accomplish anything. I can find my acceleration here by using that the acceleration is mu sub k times g times the cosine of 20 plus g times the sine of 20. This ends up giving me an acceleration of 5.19 meters per second squared, and that's down the incline. Now I want to know how fast is the box going after 2 meters. I'm going to use this equation for this because this is the easiest way to do it. Love this equation because it's so easy to do because we don't have to use time. In this case though, I want to make the a negative because of the fact that it's down the incline. So notice how I can change my sign convention in the middle. That's okay. V squared is equal to V naught squared minus 2a delta x. I put that negative sign out front because my initial speed is 10, but I know it's going to slow down, so I have to subtract this second term, and that's why I know that acceleration needs to be treated as negative. And the total distance I've moved is 2 meters. If I go through the calculation and I solve for that v at the top of the incline, I get that it's 8.9 meters per second. So that's how fast the box is going when it leaves. And then it's going to go through a parabolic path. So then it becomes a projectile motion problem. And I'm going to say that the y naught is this value, this location it leaves from, and it's going to go with this velocity, which is going to be at an angle of 20 degrees. So it's traveling at 8.9 meters per second at an angle of 20 degrees from an initial y position that's equal to this side of this vertical side of the incline, which is equal to 2 times the sine of 20. And that ends up to be 0.684 meters. So my V naught is 8.9, my theta is 20, my X naught is 0, my Y naught is 0.684 meters. I'm doing a projectile motion problem at this point. So my X is equal to X naught plus V naught X T. My X naught is 0. This is supposed to be a plus, it doesn't look like one. So it's 8.9 times the cosine of 20 times t. My y value, which is y equals y naught, plus v naught y t minus 1/2 gt squared. And this becomes 0.684 plus 8.9 sine of 20 times t minus 4.9 t squared. So I want to know x when it hits the ground. I can find the time that it hits the ground by letting y equals 0. So if I let y equals 0, it's y naught is 0.684. Then my v naught times the sine of 20 is 3.04. And then minus 4.9 t squared. So this is pretty messy. I'm really sorry about that, but we can use the quadratic equation to find the time. This is a quadratic right here. It's 0.684 plus 3.04 t minus 4.9 t squared. I use the quadratic equation to solve this, and I get t is 0.796 seconds. So it's in the air for about 0.8 seconds. I found x at that time would be 8.9 times the cosine of 20 degrees times 0.796. And I find that it has traveled 6.66 meters. So that's how far it travels horizontally until it hits the ground. So you can see that we used forces. I actually used one-dimensional motion type problems and two-dimensional motion type problems. So this is pretty involved. You probably wouldn't have to do both of those, but I think it's a good example of how we can combine our learning objectives from chapters 5 and from motion to solve a problem.